Now here I want to take a look at two different ideas that are very closely related. The first, I want to take a look at the time required to double an exponential growth rate. And then when I'm done with that, I want to take a look at the time required to half an exponential growth rate. So let's work through the idea of having to double something. So if I have a function f of t, where f of t has the form c naught e to the kt, and what I want to do is, where t equals time, I want to find out how long it's going to take to double the amount that I have. Now notice I said c naught earlier. The c naught was the initial value. Notice f of 0 equals c naught e to the k times 0, which is c naught e to the 0. Well, e to the 0 is 1, so that's just c naught, my initial value. So what I really want to do is I want to figure out how long it will take to double this. So that's saying I want 2 times c naught to be equal to c naught e to the kt, because this is now double what I started with. So what I need to do is simply solve this for t. Now notice the very first thing I would do to solve this, obviously, is divide both sides by c naught. And when I do, they're going to cancel out. So what I end up with is simply 2 equals e to the kt. Now notice I don't have a value for c naught in here. I didn't even say what it was. It doesn't matter. It's going to cancel out every time. So as an example, if I said, just sidetrack for just a moment, if I let c naught equals 100, so maybe I have 100 cells that I'm trying to double in a petri dish or something. What I'm really saying is, if I'm going to double it, I need to know when this model is equal to 200, because that's doubling how much I started with. Well, again, if I divide both sides by 100, it's going to cancel out. And what do I get? 200 divided by 100 is 2. So 2 equals e to the kt. So see, this initial value is totally irrelevant when I'm talking about doubling the amount that I have. So I can just solve this for 2. Now what that does, or how I would do that, is obviously I would take the natural log of both sides. So ln 2 equals ln of e to the kt. And then, of course, with properties of logs, I have ln 2 equals kt times ln e. But ln e is just equal to 1, so I can just drop that out. And remember, I'm solving for t, so that implies that t is equal to the natural log of 2 divided by k. So to actually answer this specific question, how long will it take to double? Well, I need to know this value k. So in other words, I'd have to have this part of the model known. So for any unknown value of k, I can think of this actually as t of k equals ln 2 divided by k. So for various values of k, that is how I can calculate the time that's going to take, in this case, to double. Now notice two things. Number one, if k is positive, then t will also be positive, because ln 2 is a positive number. If you look at the graph of ln, it is 0 when, in this case, t equals 1. So between 0 and 1, ln t is negative, and from 1 to infinity, ln t is positive, and it's 0 at 1. So ln t is a positive number, so if k is positive, then I'm going to have a positive value, which would correspond with a growth model. Now if k was negative, I would have a decay model, so t would end up being negative. Well, that should make you scratch your head. Well, of course, that doesn't make any sense. If I have a decay model, can I expect to double the amount that I have? No, I can't. So what this is really saying is, if you have a decay model and you're trying to figure out how long it's going to take to double something, it's going to take negative time, meaning there is no solution. It doesn't make any sense. You're dealing with a decay model. So actually, let's go ahead and look at the decay model now. What's the time required to half an exponential growth rate? Well, that's going to be the exact same idea. If I have the same model, say f of t equals c naught e to the kt. Now, if this is a decay model, it's going to have to be a decay model actually to get a half, because that's less what I had. If the growth rate is positive, it's a growth model. If the growth rate is negative, then it's a decay model. So to half it, all I really need to do is set this equal to 1/2. Because to half it, that really means what I have is whatever c naught is, I need to divide it by 2. That has to be equal to c naught e to the kt. Again, if I divide both sides by c naught, the initial value is going to cancel out everywhere. And again, I'm left with 1/2 equals e to the kt. So if I wanted to triple it, I would just set this equal to 3. If I wanted to find out how long it takes to end up with 1/4 of what I started with, I'd set this equal to 1/4. Same idea. So now, obviously this has to be a decay model because I'm looking at 1/2 of what I started with. So I know that k is actually going to be a negative number. So I'm going to take the log of 1/2 equals the log of e to the kt. That then implies that log of 1/2 equals kt times log e, but of course log e is 1. So that would imply that t is equal to log of 1/2 divided by k. Now remember, k is a negative number. Log of 1/2 is also a negative number. Again, look at this graph of log. Natural log, here's 1. So 1/2 is over here somewhere. I'm going to end up with a negative value on the y-axis. So ln is going to be a negative number. K is going to be a negative number. Negative over negative gives me a positive, so time will be positive, which again makes sense if I take a look at the decay model. Just very briefly here, this is a reminder, decay model is going to look something like this. Here's my initial amount. Somewhere right about here, I'm going to have half as much as I started with, so I'm really looking for is this value of t that gives me half as much as what I started with.